So today, good morning, yay! More of them, I always appreciate those. How does natural log help in integration? That's what we're gonna look at today. Because we looked at differentiation Monday, we did it Monday. Today we're gonna look at integration. And since they're inverse operations, shouldn't be too bad. So we're learning to use natural log to aid us in integration. We'll be successful when we can integrate more functions by identifying patterns, which is, again, most of what differentiation and integration are, is looking at what patterns we have and how we can use them from there. Boom. So there it is. That's all for today. But 1 over cabin d cabin gives you natural log cabin plus c, which really a natural log cabin plus c probably would give you a houseboat made of logs. I just needed to let that sit for a little bit so you can think about how bad that was. But this is basically the rule just as a joke. So let's actually go past that. There's practice. Nah, just kidding. Here are the actual integration rules that we use for logs, in particular natural log. Is there something for the other logs? Yeah, but we're not going to look at that yet. We'll look at that in a future lesson. But here are rules for integrating using natural log. The indefinite integral of 1 over x dx is the natural log of the absolute value of x plus c. So there's a slight difference here. When we defined natural log, we said natural log was the integral from 1 to x over 1 over t dt, t greater or x greater than 0. And that's something I want to point out here, is that when you integrate, go backwards, we're starting with the function that doesn't have a restricted domain to something normally natural log can't be negative. Well, when we put the absolute value in there, it won't be negative. So technically, this gives us something that looks a little bit different than just natural log. So instead of just the natural log going off to the one side, technically we go off to both sides. But that is not the most important piece. The most important part is that 1 over x dx, the antiderivative of that is natural log of the absolute value of x plus c. Now, a lot of the time we don't need to write the absolute value part because it's implied we're only working with positive numbers. But if there's any implication you might be working with negative numbers, you need to keep that absolute value in there. All righty. This bottom one, it's like the same thing. Oh my gosh, except there's a u in there. And again, the u is just pointing out the fact that we might use u substitution to help us figure out things. So sometimes you look at something and you're not sure how to tackle it, and using u substitution can help us look at the pattern and see what's going on. That's it. There's practice. Do soon. These jokes work so much better when we have 50 minutes sitting in front of us and I'm like, I can go. And then I actually walk away for about 15 minutes, but. So let's do 2 examples, show you kind of how these work out. There's a couple extra in the post credits and the book for more examples and some more information about the trig rules, which trig rules I think are super interesting. And we briefly saw them at the end of the year last year in pre-calc. But again, depending on how end of the year pre-calc went for you, you may or may not have done anything with them, depending on how you chose to tackle that. And I'm not going to judge you on it because, I mean, this whole thing is really hard. Everything going on is just shit. So that's recorded. Whoops, whatever. Anyways, we're all just trying the best we can. So let's try this one together. So trying to find the antiderivative of 5 over x dx. Well, I'm going to bring the 5 out front. So this looks exactly like the natural log rule we have for integration. It looks exactly like it. Right? Exactly like it. So that means that it'll be 5 times the natural log of the absolute value of x plus c. That's a nice little one-stepper. Good place to get your feet wet. Ooh, mean, we are on a natural log houseboat. So, I mean, getting your feet wet may or may not be a good thing. If you're intending to get your feet wet, good. If you're not, and you're on the upper level, you might be sunk. All right, let's try this one. So I'm gonna pull that 2 out front. Again, you don't have to pull those constants out front, but when you're first starting and looking for patterns, it's helpful to pull constants out front. Can't pull variables out front, remember that, but you can pull constants, okay? So I'm gonna pull this constant out front. This almost looks like the rule we used over here, but it's just a little bit different. So I think I'm gonna use U substitution to kind of rewrite that, to say that there's probably a function and a function here. So I'm gonna say, let's let U equal 3x minus 1, which would be that piece right there, which would be ideal because then I have 1 over U, which looks exactly like the rule that we have, which is pretty great. So then du, taking the derivative and solving for du, we get this. To make my life a little bit easier, I'm just gonna solve for dx and see what happens. So I get dx equals 1/3 du. If I plug those things in, let's plug in u and dx in the respective spots. I get this. Notice now it's 2/3 out here because I felt like it. And when I substituted in 1/3 du for dx, I would get 1/3 du, and I brought the 1/3 out front because again, it was a constant. You can do that with constants that are multiplied a bunch of other things. So now I have 2/3 integral of 1 over u du. Hey. Just a moment. Oh, all right, good question. How did I get the du equals 3dx? Okay, annotate, show. So what I did to get from here to here is I did the derivative with respect to x to both sides of this. So the derivative of u with respect to x is, whoa, that looked terrible. Du over dx equals 3. But it's not helpful to leave it as du over dx, so then I multiply by dx to get du equals 3 dx. Good questions. Thank you so much for asking. Okay, so that is how we got this part. Again, just to make sure I'm super clear, to get down here, we divided by 3 to get dx all by itself. And again, this 3 down here is from this 1/3 that we pulled out front because we could. Got it. So there's an intermediate step that I didn't show to go from here to here. So if I was to show that intermediate step, which let's do in green, which would go right here. It is to say we'd have 2 over the indefinite integral of 1 over u times 1/3 du. I'm really not that good with writing it with this mouse yet. Oh, annotate. So this piece came from right here. Oh. Just a quick thing there, folks. All right. Ooh, I'll answer that in a moment. So that's where the 1, and then what I did is I took the 1/3 and I just brought it out front as a coefficient. because it's just 1 over u times 1/3 times the u. It's only multiplication. And because of that, I can take the constant and just bring it out front to help see the patterns easier. Where did the 2 come from? The 2, right now my drawing tools are kind of in the way. Oh, there's the 2. Oh, here, let me actually remove my drawing tools for a hot sec. The 2 came from right up here. See, it was 2 over 3x minus 1, and I just brought the 2 out front so I could try to simplify the way it looks, so I could look for and utilize those patterns that I mentioned in the previous slide. Awesome. Thank you so much for those questions. All right, now let's clear those drawings and finish that off. All right, there we go. Clear drawings, finish it off. This looks like our rule. So 1 over u du, the antiderivative of that is natural log of the absolute value of u plus c. We're almost done, except u wasn't the variable we started with. So let's change it back to x, which in this case is we're using this expression right here. And that's my final answer. Cool. There's 2 more examples. And a lot of these, as we get more and more trig stuff further in the year, or just integration stuff, we're going to see a lot of things that look similar. So the big thing is you can know your patterns and keep trying to look for them and apply them. Woo! Here's another one that I wanted to look at because I thought this one was really interesting how it worked out. So looking at this doesn't immediately look like the one we were just doing. It doesn't look like it might be that natural log. But I also look at that and I'm like, I'm not really sure how to progress. So, because I can't break the bottom apart. I think what I'm going to try is use substitution to see if that can help me rewrite this. So if I let u equal x plus 5, that'll give me the bottom, sweet. Du equals dx, I'm able to switch out those. The problem is, what do I do up here? Well, in 4.5, we talked about when you write this equation for u, you could also solve it for x and substitute that in. And if I solve this u equation for x, I get u minus 5 equals x, which allows me to rewrite this bad boy integral up here with this one. This one, it's much more preferential to have 2 terms on the top and 1 term on the bottom, because we can split that fraction apart much easier than we can this one. We can't really split this one apart. There's not really a whole lot we can do there. Here, we have options. So let's use those options. Because we can split it apart, because there's that operation happening in the numerator, we can rewrite it as u over u minus 5 over u, and then u divided by u is 1, so that's where that goes, right? U divided by u gives me 1. So 1 minus 5 over u, du. This we can handle. We can find the antiderivative of this. Now, the new rule we're looking at today, that integrating using natural log, is only really affecting this part right here. And again, so this is subtraction, we can do the integration separately. So if the antiderivative of 1 with respect to u is u, the antiderivative of this one would be 5 times the natural log of the absolute value of u plus c. Always plus c because we're on the ocean. Planet's 90% water, something like that. So really we're always floating, kind of, maybe, not really. I don't think that's how any of that works. Anyways, there's this. Again, to highlight where everything's coming from. U is the antiderivative of 1 with respect to u, du, right? Colors. Let's go green again. Careful. There it goes. I'm getting better at drawing. So the antiderivative of 5 over u with respect to u is 5 natural log of the absolute value of u. And then since it was subtraction, we'll keep the subtraction. We always do a plus C when we do indefinite integration because you don't know. There could have been a constant. There may be, there might not be. But the important thing is that there could have been, so we have to account for it. And if we don't account for it, everything is terrible and life falls apart. All right, clear drawings. Because again, when we're doing indefinite integration and we use substitution to help us out, we always want to end with the same variable we started. If this was a definite integral, it doesn't matter. We're looking for a numerical answer at the end anyways. But this is not a definite integral, so I don't care. I want to make sure it's back in the same variable that I started with. So there's some cool integrals when it comes to trig. Antiderivative sine of u du is negative cosine of u plus c. Yeah, that's something that we've seen for a while. That's not terribly new or crazy. Antiderivative of cosine of u du is sine of u plus c. Again, nothing terribly wild or crazy. This one's new to us because it's this section where we start looking at that. We know what the derivative of tangent is. It's secant squared. Like the derivative of tangent of x is secant squared x. But as you can see, the antiderivative of tangent isn't the same thing. In fact, the antiderivative of tangent is negative natural log of the absolute value of cosine plus c. Similar argument can be made with cotangent. Cotangent of u du equals the natural log of the absolute value of sine of u plus c. Again, I'm using u here to say that whether u is equal to x or u is equal to something else, that we can do this integration regardless of what the variable is. All right, that's a big takeaway here. Now, this one I want to point out. These top four we can do or reason out, and the justifications aren't too wild. In fact, do this, like tangent, remember, is a ratio. That one's sine over cosine. And if you set that up as let u equal cosine, because that's what's in the denominator, it'll work out. And you can use the log rule to do the antiderivative of that. Similarly here, cotangent is cosine over sine. So if you let for this one, u equals sine, then again, log rule works for that. So those ones are kind of more, those ones are interesting and they're worthwhile to kind of play out and try to do. I gave you the setup. This is the big revelation to rewrite it as sine over cosine and cosine over sine. And then you can use u substitution to work those two out and see why those two should be. These four, again, are ones you should know. And the first two you definitely should know already. If you don't know the bottom two, that's okay. We're introducing them today. Today's the day that you're going to start working on learning those, so you know those. So it's fine. It's all good. All right, I'm going to clear those. Now, these bottom two are a little more difficult to remember because there are antiderivatives of cosecant and secant. Again, there's patterns that you can remember for those and how they work. They appear less frequently because there's like a trick you have to use in order to make them work. Even off the top of my head, like I should have gone and looked it up before I talked about it today, but I don't remember how these ones work. I know that it involves rewriting it as 1 over sine and 1 over cosine. And then you have to add or subtract something to make something happen for you. But again, there's like a involved process in order to make it happen. If you read through your book, and you should read through your book for each section, it'll walk you through the process of why these two are what they are. Okay. But these top four are the ones that are most important because they're the first two we've been doing for a while in a sense. And these two are simple enough to be done that once you do them once, you're like, oh, okay, that's just natural log and I can remember that. But you need to, it's a good thing to know because that's more likely to show up on the test because it's something you could reason out. All right. These, you might need to know them, but if you don't remember them, it's not going to probably be the end of the world. This is actually it today, other than reading the section. So here's actually the problems. Again, they're due soon. A couple people asked me last class, and again, like I'm going to put like due dates up in Schoology. Those due dates are basically for anyone who likes having a due date to help them get motivated to get something done. But the general idea is just when you get them done, turn them in. I'm going to try about every 1 to 2 weeks, just kind of update what I've got from you. So you know what I miss, what I have and what I don't. I'll start, oh, did I put assignments in Schoology yet? I don't think I put any assignments in Schoology yet, so I should go do that. In fact, I shall go do that shortly after I'm finished recording this.